Welcome back, everybody. Today, we're going deep on a concept that's, well, honestly, it's pretty mind-bending.
Yeah,
Quantum singularities.
I know, right?
Your source material basically lays out a new way to look at the universe.
Yeah.
And it all starts with these things called quantum singularities. That
Mhm.
might be the most fundamental building block of reality,
Yeah,
even more basic than atoms
totally.
or electrons. We're
Mhm.
talking about potentially the key to unlocking the mysteries of dark matter,
Huge.
dark energy,
Yeah.
and even the very beginning of the universe itself.
That's a big one.
It's a big one.
It's an incredibly ambitious idea.
Oh, yeah.
Your source material actually lays out an experiment
Okay.
that's designed to recreate the conditions of the Big Bang.
Wow.
And it uses these quantum singularities as the foundation.
That's amazing.
It's a fascinating combination of theoretical physics and experimental ingenuity.
So before we get to that experiment,
Right.
let's break down the basics here.
Yeah.
What exactly are these quantum singularities?
Right.
The source material keeps mentioning that they exist everywhere and nowhere at the same time.
Mhm.
What does that even mean?
Yeah, it's a challenging concept to wrap your head around for sure.
Yeah.
Instead of thinking about them as physical objects,
Yeah, okay.
think of them as points of immense energy potential
Right?
that are woven into the fabric of space-time.
Okay.
They're not bound to a specific location,
Right.
like a planet or a star.
Okay.
They're more like a fundamental property of the universe itself,
Mm-hmm.
existing as a potential at every point.
So not a thing.
Right.
But
yeah.
like a property.
Yeah.
Like the universe has a certain quantum singularityness
Exactly.
at every point, and that's what gives rise to everything.
Yeah, that's a great way to put it.
Okay.
And the source material takes this a step further and suggests that these quantum singularities, or QS, as we'll
Right.
call them,
Got it.
might have actually predated the Big Bang itself. They could be remnants of a pre-time energy state,
Wow.
holding the secrets to what existed before the universe as we know it.
Okay, now we're venturing into serious cosmic mystery territory here.
Yeah.
So if these QS are everywhere
Mm,
and make up everything, how do we even begin to study them?
right.
I mean, they're invisible.
Right. That's where the experiment we mentioned comes in.
Okay.
But before we dive into that,
Yeah.
we need to understand two key tools that the source material lays out:
All right.
the quantum singularity energy equation
Mm-hmm.
and the charge matrix model.
Okay.
These are going to be essential for grasping how the experiment works
Okay.
and what it hopes to achieve.
All right, let's start with the equation.
Yeah.
It's pretty intimidating at first glance,
It looks that way.
but hopefully we can break it down.
We'll try.
What can this equation actually tell us about these quantum singularities?
So at its core, the equation, which looks like this, not the 100 plus 1, describes how much energy each QS possesses.
Okay.
It might seem complex,
It does.
but it combines some familiar concepts.
Okay, good.
You've got Einstein's famous EMP, representing the energy locked up in mass.
Mm-hmm.
And then you have the quantum energy of particles,
Right.
represented by A.
So it's merging the energy of something massive like a planet
Yes.
with the energy of something tiny like a photon of light.
Exactly.
Wow.
It's saying that both of these forms of energy contribute to the overall energy of a QS.
Okay.
And what's truly mind-blowing is that this equation suggests that QS can actually draw energy from space-time itself.
Whoa. Hold on.
It's wild.
They have like little power plants running on the fabric of reality.
It's something like that, yeah.
That's a concept I have not heard before.
Yeah.
So we've got these potentially universe-creating QS,
Yep.
and they're powered by space-time itself.
Seems that way.
What about the charge matrix model?
Yeah.
Where does that fit in?
So the charge matrix model is all about predicting how different elements will behave within this proposed experiment,
Yep.
particularly in this quantum singularity field.
Mm-hmm.
It takes into account things like an element's electron configuration,
Okay.
the type of chemical bonds it forms,
Mhm.
and even the distance between electrons and the nucleus.
So it's like assigning a personality profile
Yeah.
to each element based on its quantum properties.
That's a great analogy.
Cool.
And here's where it gets really intriguing.
Okay.
The model suggests that how these elements connect can either reinforce QS stability,
Okay.
creating what they call coherent bonds,
Mm-hmm.
or disrupt it,
Okay.
leading to decoherent bonds.
So the structure of matter itself could actually be influencing the stability of these quantum singularities.
That's what they're proposing, yeah.
That's a wild idea.
It is.
But wouldn't that mean that even the smallest change in atomic structure could have huge implications for the universe as a whole?
Yeah, potentially.
I mean, that seems like a lot of power.
It is a lot of power.
For tiny atoms.
Yeah, you're picking up on the key point here. That's exactly what the researchers are trying to investigate.
Okay.
And that brings us to the experiment itself.
Okay.
Because this is where they plan to test these ideas
Yeah.
and potentially witness these effects firsthand.
All right, this is where things get really interesting. I think we've got a good grasp of the basics now.
I think so.
So let's dive into this experiment.
All right.
How are they actually planning to simulate the Big Bang and study these quantum singularities in a lab?
Well, it all starts with creating an environment
Okay.
that mimics the conditions of the very early universe,
Okay.
just fractions of a second after the Big Bang.
Wow.
To do that, they're going to use something called a Bose-Einstein condensate,
Okay.
or BEC.
I've heard of those. It's like a state of matter where atoms are cooled down to almost absolute zero and start acting like one giant quantum wave, right? But how does that help us recreate the Big Bang?
It's all about creating a low-energy state,
Okay.
similar to the early universe.
Got it.
The BEC acts as a kind of quantum medium
Okay.
in which the researchers can introduce different gases, like hydrogen and helium,
Okay.
and observe how they interact with the QS field.
Okay, so we've got our simulated early universe in the form of this BEC.
Right.
And then we introduce different elements to see how they behave.
Yeah.
But wouldn't those elements also have their own quantum properties?
They do.
How do the researchers differentiate between the effects of the BEC,
Yeah.
the introduced elements, and the QS field itself?
That's where the ingenuity of this experiment really comes in.
Okay.
They're not just observing how the gases behave.
Right.
They're using targeted tools to probe the QS field directly.
Okay.
We're talking about electromagnetic pulses at specific frequencies, and even the manipulation of gravity itself.
Hold on, manipulating gravity. That sounds like something straight out of science fiction.
It does, right?
How is that even possible?
It's not anti-gravity boots or anything,
Okay.
but it's still pretty incredible.
Yeah.
The idea is to use controlled magnetic fields, but to create variations in the gravitational force within the BEC.
Okay.
By doing this, they can actually simulate the conditions that led to the formation of galaxies in the early universe.
So it's like creating a miniature universe in a box, complete with its own mini galaxies?
Kind of, yeah.
That's amazing.
That's pretty cool.
And they're doing all of this while carefully controlling for any external influences.
Right.
Using a Faraday cage,
Yeah,
right?
exactly.
To make sure they're only observing the effects of the QS field and nothing else.
That's the goal.
Okay.
But the real key to this experiment is how they plan to actually observe those effects.
Okay. How's that?
They're going to be looking for something very specific.
What? Resonance.
Resonance. Like when a singer hits a high note and shatters a glass.
Kinda. Yeah.
What does that have to do with quantum singularities?
It's a similar concept, but on a much smaller scale.
Okay.
The researchers believe that by applying electromagnetic pulses at specific frequencies...
They can hit the sweet spot for the QS field,
Okay.
causing it to resonate
Okay.
and reveal its hidden properties.
Interesting.
They predict each element will have its own unique resonance frequency.
So by observing how the QS field reacts to these pulses and how it resonates with different elements, they can gain insight into its behavior and its influence on the universe.
Exactly.
That's a pretty clever approach.
I think so too.
I'm starting to get really excited about this experiment, but I have to ask, how will they actually know if they've seen a QS?
Right.
What kind of evidence are they looking for?
Well, they'll be using an array of highly sensitive instruments to monitor the BEC,
Okay.
but they also have a more visual technique up their sleeve,
Oh, okay. What's that?
something that uses fog.
Fog. Like the kind that rolls in on a spooky night.
Not quite that eerie, but it's still pretty fascinating.
How can fog help us see quantum effects?
Think of the fog as a canvas for the quantum world. The researchers believe that if QS are present and interacting with the gases and the BEC, it will actually create distinct patterns in the fog,
Interesting.
like tiny ripples or waves.
So they'll be looking for these telltale signs in the fog.
Yeah.
Evidence that something truly extraordinary is happening at the quantum level.
Exactly.
That's incredible. I can't wait to hear what they find.
It could be interesting.
But before we get ahead of ourselves,
Yeah.
let's talk about what this experiment could mean for our understanding of the universe.
Okay.
If they actually observe these QS, what kind of implications could that have?
Well, that's where we get into the truly mind-blowing possibilities.
Okay.
Because if this experiment succeeds, it could revolutionize our understanding of everything.
Wow.
From dark matter to the ultimate fate of the universe.
Okay, now I'm really hooked.
Right.
Let's dive into those implications.
Let's do it.
Let's start with dark matter.
Okay.
Remember, it's this mysterious substance that we can't see directly, but know must exist because of its gravitational effects on galaxies
Right.
and galaxy clusters.
Exactly.
Right. It's like the cosmic glue holding everything together.
It is.
And what if instead of some exotic, unknown particle, dark matter is actually these quantum singularities shaping the universe from the very beginning?
That's the question.
So these tiny QS woven into the fabric of space-time could actually be the source of the gravity that holds entire galaxies together.
It could be.
That's a pretty wild thought.
It's a bold idea.
Yeah.
But it's one of the most exciting possibilities that this experiment could explore.
Yeah.
Imagine a universe where the scaffolding of reality is made up of these tiny, energetic QS, their collective gravitational pull shaping the cosmos as we know it.
That would completely change our understanding of the universe. But what about dark energy?
Okay.
That force that's supposedly pushing the universe apart at an accelerating rate. Could this experiment shed any light on that as well? How?
Remember how the charge matrix model predicts that certain interactions between elements in QS can lead to decoherence?
Yeah.
Well, the researchers believe that this decoherence process could be linked to dark energy.
So as these QS interact and lose coherence over time, it actually creates a repulsive force that pushes the universe apart.
That's the theory.
So instead of just gravity, we have these dueling forces, coherence pulling things together and decoherence pushing them apart, shaping the universe's evolution.
Think of it as a cosmic tug of war.
Okay.
With the fate of the universe hanging in the balance.
Wow. So this experiment isn't just about observing QS. It's about understanding the very forces that are shaping the universe's destiny.
It's about the big picture.
This is getting pretty heavy. I think we need to take a step back and really break down each stage of the experiment and what they hope to observe.
All right.
Where should we begin?
Let's start with the introduction of hydrogen gas into the BEC.
Okay.
This is where we really start to see the quantum singularity energy equation and the charge matrix model in action, and where the experiment really begins to mimic the conditions of the very early universe.
It sounds like a good place to start.
Yeah.
Let's unpack that in part 2.
Let's do it.
All right, we're back and ready to dive into the specifics of this incredible experiment.
Okay.
We left off talking about the first stage where they introduce hydrogen gas into that supercooled Bose-Einstein condensate.
Right.
Why hydrogen first?
Well, remember the charge matrix model. Hydrogen being the simplest element, which is 1 proton and 1 electron.
Right.
Has a very straightforward profile.
Okay.
The model predicts that it'll have a high coherence factor.
Okay.
Meaning it's going to readily interact with that QS field.
Okay.
We're talking rapid fluctuations and phase shifts. Almost like a quantum frenzy.
So if the BEC is like a calm pond,
Yeah.
dropping hydrogen in is like throwing a handful of pebbles in, causing ripples and disturbances all over the surface.
Exactly.
Except instead of water, we're talking about the fabric of space-time itself being disturbed, right?
That's the idea.
Wow.
And the researchers believe this chaotic energy is a close approximation of what the universe was like.
Okay.
Just fractions of a second after the Big Bang.
Wow.
A period of immense energy and instability, where energy was constantly converting between mass and pure quantum states.
So we're not just observing hydrogen atoms floating around in a BEC.
Right.
We're potentially witnessing the echoes of the Big Bang itself.
In a way, yes.
Incredible. But I'm guessing things don't stay chaotic forever.
You're right.
What happens next?
In the second stage, they introduce helium into the mix.
Okay.
Unlike hydrogen, helium, with its full outer shell of electrons,
Right.
is much more stable.
Okay.
The charge matrix predicts a higher decoherence factor for helium,
Okay.
meaning it'll actually help to stabilize the QS field.
Interesting. So it's not about eliminating the quantum fluctuations altogether,
Right.
but rather introducing a counterbalance. Is it fair to say the helium is like adding oil to those choppy waters?
Yeah.
Smoothing things out and bringing a bit of order to the quantum chaos.
That's a great way to visualize it.
Cool.
And this stage is particularly intriguing.
Oh, why is that?
Because it potentially simulates a crucial event in the early universe called nucleosynthesis.
Nucleosynthesis.
As the QS field stabilizes thanks to helium, it could be mimicking the conditions that allowed the very first atoms to form.
Wait, hold on.
Yeah.
We're talking about recreating the process that created the building blocks of matter.
Potentially, yes.
As we know it.
It's a big idea.
Right here in a lab.
That's the hope.
That's a pretty huge implication. Are we actually going to see atoms forming from pure energy?
We'll not directly observe the atoms themselves forming,
Okay.
but the way the QS field reacts to the introduction of helium
Okay.
could provide valuable insights into the dynamics of nucleosynthesis.
Okay.
Remember, we're talking about an incredibly complex process that occurred billions of years ago.
Right.
And we're just beginning to understand the forces at play.
So it's not about creating a mini sun in the lab,
Right.
but rather about observing the subtle energy shifts and changes in the QS field
Exactly.
that might mirror the conditions that allowed the first hydrogen and helium atoms to form.
That's the goal.
It's like looking for the fingerprints of the universe's earliest moments. Okay, we've got hydrogen creating chaos,
Yeah.
helium bringing stability.
Right.
What happens when you mix them together?
Good question.
Do they just cancel each other out?
That's the beauty of this experiment.
Okay.
It's not about simple cancellation.
Okay.
When you combine hydrogen and helium in the third stage,
Yeah.
the researchers predict a dynamic interplay
Okay.
between stability and fluctuation.
Okay.
Remember, hydrogen wants to create chaos,
Right.
while helium wants to maintain order.
Yeah.
The QS field becomes a sort of quantum battleground.
A battleground.
And this is where we might really start to see the emergence of complex structures.
So it's not just about the individual properties of hydrogen and helium,
No.
but about how they interact with each other.
Yes.
And with the QS field as a whole.
Exactly. It's like observing a delicate dance
Okay.
between order and chaos.
Interesting.
And it's in this dance that the researchers believe they might glean insights into how the universe transitioned
Okay.
from a state of pure energy to the structured cosmos we see today.
This is reminding me of that famous saying, order arising from chaos.
That's classic.
Okay, I'm picturing this quantum tug of war between hydrogen and helium playing out.
Yeah.
But something tells me we're not done yet.
We're not.
What's the final element they introduce and why?
In the final stage, they bring in xenon,
Okay.
which is significantly heavier than hydrogen and helium.
Right.
It's here that we really start to explore the concept of charge asymmetry.
Charge asymmetry. So we're not just talking about energy and stability anymore, but about a fundamental imbalance in the universe. What does that even mean in this context?
Think about it this way. The universe isn't perfectly symmetrical.
Okay.
We've got more matter than antimatter.
Okay.
Galaxies cluster in uneven patterns.
Right.
And even the cosmic microwave background radiation shows variations.
Okay.
It's a mystery that has baffled physicists for decades.
Okay, so we know the universe is a bit wonky.
Yeah.
But how does xenon tie into all of this?
Well, xenon, due to its complex electron configuration, is a key player in creating charge asymmetry within the QS field.
Okay.
Its presence disrupts the delicate balance achieved by hydrogen and helium, introducing a new level of complexity.
So more chaos.
You could say that.
Okay.
The researchers predict that this will lead to the formation of structured charge asymmetry within the BEC.
So we're not just talking about random fluctuations anymore,
Right.
but about the emergence of distinct patterns of charge imbalance.
Exactly. And if they observe this, it would be a huge step towards understanding why the universe itself is so asymmetrical.
Wow.
It could be that these tiny quantum singularities, influenced by the presence of heavier elements like xenon, played a role in shaping the uneven distribution of matter and energy that we see today.
It's mind-blowing to think that these tiny interactions happening in a lab could potentially hold the key to understanding the large-scale structure of the universe. But I have to ask, with all these elements and forces at play, how do the researchers even begin to make sense of what they're observing?
That's where those electromagnetic pulses, or EMF, come in.
Okay.
Remember, the researchers believe each element has a unique resonance frequency within the QS field.
Okay.
By applying these EMF pulses at specific frequencies, they can essentially tune in to different aspects of the experiment.
So it's like having a cosmic radio dial.
Yeah.
And they're turning the knob to see how the QS field reacts to different frequencies.
It's a great analogy.
Wow.
And by mapping these resonance points, they can essentially create a fingerprint
Okay.
of how QS interacts with different elements under different conditions.
It's like deciphering the language of the quantum world. Okay, I think we've covered the basics of each stage.
Yeah.
But I'm still stuck on this idea of seeing QS in the fog.
Okay.
Can you elaborate on that a bit more?
Sure. Imagine this, the BEC is housed in a special chamber.
Okay.
And they introduce a fine mist of fog into the chamber.
Okay.
Now, if QS are present and interacting with the gases in the BEC,
Yeah.
the researchers believe those interactions will create disturbances in the fog,
Interesting.
creating visible patterns.
So it's like the fog is acting as a screen,
Uh-huh.
and the QS are projecting their activity onto it?
Yeah, kind of.
We'd be able to actually see the quantum world in action?
That's the hope.
Wow. What would these patterns look like?
That's the exciting part. We don't know for sure.
Oh.
The researchers predict they might see things like tiny ripples or waves, or perhaps even more complex patterns that reflect the underlying structure of the QS field.
It's like we're trying to glimpse a shadow puppet show being projected from the quantum realm. Okay, so we've got our experiment.
Right.
We've got our elements.
Yeah.
We've got our EMF probes. And we've got our fog screen.
We've got it all.
What happens next?
Well, the potential implications of this experiment are truly vast.
Okay.
It could provide insights into the nature of dark matter and dark energy, help us understand the asymmetry of the universe,
Okay.
and even give us clues about the universe's ultimate fate.
Okay, now I'm really on the edge of my seat. Let's unpack those implications. What would it mean if they actually observe these quantum singularities
Right.
and see them creating these patterns in the fog?
Yeah.
What would that tell us about dark matter?
Well, let's start with dark matter.
Okay.
If the patterns observed in the fog
Yeah.
match the predictions based on the quantum singularity energy equation and the charge matrix model, it would provide strong evidence that QS could in fact be the source of the missing mass we call dark matter.
So instead of some mysterious invisible particle,
Right.
we're talking about a fundamental property of space-time itself,
Yeah.
acting as the gravitational glue holding galaxies together.
Potentially, yes.
That's a pretty huge paradigm shift.
It would be.
What about dark energy?
Okay.
What clues could this experiment offer about that mysterious force?
Well, remember that idea of decoherence we talked about?
Yeah.
The weakening of the QS field over time.
Yeah.
Well, if the researchers observe specific patterns of decoherence
Okay.
that correlate with the accelerating expansion of the universe, it could be a major breakthrough in understanding the nature of dark energy.
So we'd be witnessing the very force that's driving the universe apart.
We could be.
That's incredible. But there's more, right?
There is.
Didn't you mention something about the universe's fate?
I did.
Can this experiment really tell us whether the universe will keep expanding forever or eventually collapse back in on itself?
It's a question that has fascinated cosmologists for centuries.
Yeah.
And this experiment might offer some tantalizing clues
Okay.
by studying how QS coherence decays over time in the lab,
Okay.
and by observing the interplay between coherence and decoherence. The researchers could potentially extrapolate those observations
Yeah.
to the universe as a whole.
So this tiny experiment using fog and electromagnetic pulses
Yeah.
could actually give us a glimpse into the distant future of the universe.
That's the hope.
That's mind-blowing. But it all hinges on whether they actually observe those quantum singularities in action, right? What are the chances that this experiment actually works?
It's important to remember that this is all still theoretical.
Okay.
It's a tremendously ambitious project.
Yeah.
And there's always a chance they won't observe what they're hoping to see.
Right.
But even if they don't directly observe those telltale patterns in the fog, the experiment itself will be an incredible feat of engineering and scientific ingenuity,
Okay.
pushing the boundaries of our understanding of the quantum world.
So it's a win-win either way.
Exactly.
Either they make a groundbreaking discovery that revolutionizes our understanding of the universe,
Yeah.
or they pave the way for future research and open up even more fascinating questions. All right, we're back, and I gotta say, after that deep dive into the experiment itself, my mind is reeling with the possibilities. We've talked about dark matter, dark energy, the fate of the universe. It's almost too much to process. But let's try to bring things back down to earth for a moment.
Right.
If this experiment actually works, if they actually observe these quantum singularities, and they behave as predicted,
Right.
what are the real-world implications? How could this knowledge change our lives?
That's a great question, and it's really hard to say with any certainty. You
Yeah.
know, we're talking about potentially fundamental shifts in our understanding of physics and the universe.
Right.
It's like asking Galileo
Oh, wow.
what the telescope would mean for our daily lives
Yeah.
back in the 1600s.
I like that.
You know, he could probably point to things like improved navigation and astronomy,
Yeah.
but he could never have predicted the internet or GPS.
Right, exactly. So you're saying that the implications of this experiment could be so far-reaching that we can't even fathom them yet.
Pretty much, yeah.
That's both exciting and a little terrifying.
It is a bit of both.
Okay, but that's the beauty of scientific discovery, isn't it?
It is.
We're constantly pushing the boundaries of knowledge.
Yep.
And sometimes those breakthroughs lead to unexpected and transformative applications.
That's right.
Like, remember when electricity was discovered?
Yeah.
It seemed like a mere curiosity at first,
Yeah.
but look how it has revolutionized our world.
Absolutely.
Point taken.
Yeah.
We might not know exactly how this knowledge will change our lives,
Right.
but we can at least speculate.
We can.
Let's start with dark matter.
Right.
If it turns out that QS are indeed the source of this mysterious mass,
Yeah.
wouldn't that have huge implications for our understanding of gravity?
For sure. It could lead to a whole new theory of gravity, one that takes into account the properties of QS and their interaction with space-time.
Okay.
Who knows? Maybe we'll finally be able to unify gravity with the other fundamental forces of nature.
Whoa.
Something that has eluded physicists for centuries.
Now, that would be a major scientific breakthrough. What about dark energy?
Okay.
Could harnessing this repulsive force lead to any practical applications?
It's a possibility, but it's highly speculative at this point.
Okay.
We're talking about a force that operates on cosmic scales,
Right.
shaping the very fabric of the universe.
Yeah.
Harnessing it would require a level of technological advancement that's far beyond our current capabilities.
So no warp drives or anti-gravity devices anytime soon? Probably not. Bummer. But even if we can't harness dark energy directly,
Right.
wouldn't understanding its nature have implications for fields like cosmology and astrophysics?
Oh, absolutely. It would revolutionize our understanding of how the universe evolves, how galaxies form and cluster, and ultimately, how the universe will end.
Wow.
Imagine having a more accurate model of the universe's expansion.
Yeah.
It would be like having a crystal ball
Wow.
that could peer billions of years into the future.
Okay, now I'm picturing scientists using this knowledge to predict cosmic events like the collision of galaxies or the birth of new stars. But let's not forget about the implications for our understanding of reality itself.
Okay.
If everything is ultimately made up of these quantum singularities, wouldn't that change how we view ourselves and our place in the universe?
That's a big question.
It is a big one.
And one that philosophers and theologians would likely grapple with for centuries.
Oh, for sure.
If the universe is truly a network of interacting QS,
Yeah.
it suggests a level of interconnectedness that we're only beginning to understand.
It really does.
It blurs the lines between the observer and the observed,
Yeah.
between the microcosm and the macrocosm.
It's like the universe is one giant quantum organism,
Kind of, yeah.
and we're all just tiny parts of it. That's a pretty humbling thought.
It is.
But it also raises an interesting question.
What's that?
If QS are the source of consciousness or awareness.
Now, that's a question
Yeah.
that goes beyond the scope of this experiment,
Okay.
and one that scientists may never be able to answer definitively.
Yeah,
But it's certainly a question worth pondering.
for sure.
It highlights how much we still don't know about the universe and the fundamental nature of reality.
I think it's safe to say that this experiment, regardless of its outcome, has the potential to open up a whole new chapter in human understanding.
For sure.
It's a testament to the power of scientific curiosity
Yeah.
and our relentless pursuit of knowledge.
Absolutely.
Even if they don't find exactly what they're looking for,
Yeah.
they're bound to uncover something amazing, something that will spark new questions
Oh, no, yeah.
and push us further down the path of discovery.
I couldn't agree more. This is what makes science so exciting. It's a never-ending journey of exploration.
Exactly.
And even when we think we've found an answer, it often leads to 10 more questions.
It always does.
It's a humbling reminder that we're still just scratching the surface of what's out there.
Well said. Big thanks to our listeners for joining us on this incredible deep dive into the world of quantum singularities. It's been a truly mind-bending journey, and we hope you've enjoyed it as much as we have.
It's been a pleasure sharing this journey with you all.
Until next time, keep looking up, keep asking questions, and never stop exploring the wonders of the universe, big and small.